line on study week Friday. Okay, study Friday, you hand in your project tool and then your beamer, and then cover page I will put again, and then turn it in report. Okay, and then similarly your project one correction also due on that day. So all the due date on the same day. Is it okay? Yeah. Okay. So study week Friday. Okay. Yeah.
Oh, not next. Next no.
Yeah. Yeah. Okay. Study week Friday. Everything due on that day. Okay. Also Moodle. I will set up the link also. So if you want to confirm, you come and talk to me your project first, and then I tell you what to change, and then you change it. And then there's no more like come back and forward. Okay. So if you change it, okay, then I'll give you the mark. Any other question or not? About admit, then there's no more assessment already. So our assignment 3 finished. Then yeah. Then left with final. So to prepare for this final, right, you should do the textbook exercise and then the review question, and then that will be helpful. Okay. Okay. Yeah. Okay, let's continue. So just now we stopped at the line integral. Right. So what's the line integral again? And let's say you have a surface like this, right? So you want to integrate over a curve C. Okay, you want to look at the area under the graph above the C. Okay, so last time we called this a curtain. Okay. Yeah. And then this integral here we denote by integrate over C of my function fx y f ds. Okay. So what do? We parameterize our curve. Okay, we parameterize our curve. So we need to tell you what is xt and yt, and then give the time interval from A to B, for example. Okay, then this integral here will become integrate from A to B f of st yt. Okay, and then yeah, square root times square root of x prime t plus 1 prime t dt all square. Yeah. Okay. Or if I name my curve as RT, or I can write the formula shorter, which is just integrating from A to B of f RT. Okay, square root of s prime t y prime t is the norm of r prime t. Okay. The bottom one is easier because we can extend into 3-dimensional here. I have RT equals to ST, YT, ZT, for example. Okay. Okay. Okay, next we will introduce word done. What is word done? What's the formula for word done? Any one of you take physics before? What's word done? W equals to Fs. So you have force plus displacement, right? But this one, when you do in physics, right, the displacement is in one direction. Okay, let's say this now the direction is like in 3D now, right? You want to push your for example cabinet, But the cabinet is too heavy, so you push a bit slightly forward, backward like this. So what's your work done in this case? Well, you need to measure the arc length here. Okay. So you want to do work done in 3-dimensional. Okay. So suppose my force is a vector field. Okay. The force can be written as a vector field here. Okay, which we call the force field. Okay, in this case. So we want to compute Fs. Okay, but now the x is like curvy. So whenever we want to compute the length of a curvy curve, we need to do integration. Okay, we need to use the Pythagoras theorems to like remember. So if we have this curvy line here, we can use Pythagoras theorem to estimate the length. Okay, then we make the partition. Okay, partition smaller and smaller so that the hypotenuse will approximate our curve better. So this is the dr part, f dr. So you see, f is a vector, r is also a vector. So I need to dot them together. Yeah, I need to dot them together so that I get a function from a vector to a real number, so that I can do integration. Okay. So this integration here will be simplified into this form. Okay, simplify into this form here. So when you do work done computation, okay, what do? You just integrate f1, the f1 components with dx, f2 components with dy, f3 components with dz. Okay, why? Because these fi, right? These fi's are the function from R3 to R. Okay, then you can do integration. Okay, but how do you derive this? Okay, how do you derive this? You need to do the dot product computation. Okay, to see this. This derivation is not too important, but yeah, it's not too important. Okay. Yeah, it's not too important, but this final form is the most important one. Okay. Because when you do the dot product, so okay, so maybe I should write it down better. So let's write like this. So let's see this derivation quickly. So what is FDR here? Okay, so F is defined to be the vector F1 XYZ. Maybe we just throw away the SYZ first, just keep F1, F2, F3 dot with the derivative of R. So you differentiate in the R direction. So this is what ST, YT, ZT. Okay. 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 So what is D of these things? So I should get something like this. F1 DST plus F2 DYT plus 3 DZT. Then, and then this is what we get here. Yeah. Okay. Yeah. But another interpretation is, remember, we have a curve, right? If we have a curve, we differentiate at each point. What does it mean? That's the velocity of the curve. Correct. I have a curve, I differentiate the curve once, I get the velocity. I differentiate twice, I get the acceleration. So velocity is equivalent to what? Is a tangent vector. Okay, it's a tangent vector. Okay, so that's why that we write r prime t into this tangent vector here. Okay, yeah. Okay, okay. So let's skip this, or maybe skip this. Okay, so let's try and calculate the work done here. So we have a vector field fxy equals to s squared I minus xy. Okay, so they plot it for you already. Okay, you can see that away from the origin, the force getting bigger and bigger. Okay, and then it is in the direction. So if you stay on this first quadrant here, it is in the direction from the top left to the bottom right. Okay, top left to the bottom right. And then you want to see what's the work done by the force in moving a particle along the way from where? From 1, 0. Okay, from 1, 0 to 0, 1. Okay. So you see, this one is a bit tricky here, you see. The force is going downward, but the movement is going upward. So what do you expect? What can you expect here? Why? No, I mean, usually when you do work, right? When you go to push the work forward, the things also move forward, right? But this thing move backward. So the work done will be negative. Okay, let's see whether this work done will be negative or not. Okay. Okay, so what's the method we teach just now? So how to compute this work done? dx, dy, dz. Okay, so we split into 3 components, all the components. Okay, so here we have 2 components. So we split into 2 components here. So f1 dx plus f2 dy. Okay, we split into components first. Okay, so the story is I do the work, I split the work down into 3 components, all the components. Okay, this is the result of the dot product. Okay, so what's this here? So have we parameterized the curve yet? So we are given the parameterization. Let's write down the parameterization. So cos t I. So maybe we write in the vector form, cos t and sin t. Okay. And then t is going from 0 to pi over 2. Okay. Okay, right. So what is f1 here? So f1 here is x squared dx. What is f2? Minus xy dy. Okay. All right. So this is what? This is line integral with respect to x and with respect to y. Okay. So just now we have done this. Okay. How do we do this? So the first integral will become integration from 0 to pi over 2. X squared in this case is what? Cos square t. Correct. Okay. What is s prime t in this case? Minus sine t. Okay, so we get minus sine t times dt. Okay. And then second, we have integral from 0 to pi over 2 again. Xy becomes cos t times sine t. What is y prime t in this case? Cos t. So you have cos t. Okay. So you can try to compute this. We can actually combine the two. We can combine the two, right? Okay, so become minus 2 0 to power 2 cos square t sine t. So what's the easiest way to integrate this? Substitution. Okay, you can use substitution. U equals to cos t. Okay, and then you can get 2 integrating from 1 to 0. You can do integration by substitution. Let u equals to cos t. Again, this becomes what? 2 of u cubed over 3 from 0 to 1, which is negative 2 over 3. Okay. Any question for this? Question? Okay. Okay. So let's try and work out from the first definition. Okay, what's the first definition? So this one is the first method. Second, from definition, what do we have? Okay, from definition, work done equals to integrating the vector field dot with my changes in the curve. Okay, so let's do this start from definition. So definition says what? This equals to what? You evaluate your f at the curve, okay, dot with the tangent vector, okay, and then dt. All right. Okay. So what is this? F evaluated at RT. So your F is x squared minus xy. Okay. So you have x squared cos square t minus xy minus sine t cos t dot with r prime t. Okay, r prime t is what? Minus sine t cos t dt. Okay. So if you open up this dot product here, do you get the two items here? Okay, so first term dot with the first term. So you get cos square t times minus sine t. Okay, you get the first one. And the second one, you get minus sine t cos t times cos t. Okay, of course, you have to change this integration domain to t. So actually, we should change starting from here. So this one is from 0 to power 2, and here also 0. Because we already changed the difference in R to difference in T. Okay, so we need to change the right integration domain. Okay, no? Okay, so either you can do from the first principle here, or you can just split the work done into components wise. It's the same thing. Okay, so work done in the non-straight line path is equivalent to doing work done in 3 components. Okay, you add them up. That's all. Okay. Does it make sense? Make sense? If you want to remember formula, formula is this. Okay, on the right hand side here. You split the work done into 3 components. If you want to remember definition is this. You integrate over a dot product. Okay, integrate over a dot product. Okay, after the dot product, what happens? Actually, you are adding up in different direction. Okay. So you see, F1 only deal with dx, F2 only deal with dy, F3 only deal with dz. Make sense or not? F1 is the work done in the x direction. So of course, only when you change in dx, this work is done. Right? F2 times with dy, because F2 is the force you apply on the y direction. So only when you have a change in y, you have the work done. Right? Similarly, in the z direction. Okay? So this formula actually makes sense. Okay. Any question about this? No? Okay. Okay. So why we use dot product here instead of cross product? Because work done is a scalar, is a number. Okay. Dot product will give you a number. Cross product give you a vector. Okay, we want a number, scalar. Word done is a scalar. So that's why we use dot product. Okay, can I? So I explained this idea because so that you're easy to memorize this formula. Okay. Any question on word done? If not, we go to the next part. There's one more exercise you can try and do is this one. Okay. Yeah. Exercise. It's the same, right? So you want to compute the word done on this curve here. So you just substitute the parameterization into your force, and then you do in F1, F2, and F3 direction. Okay. 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 Next, fundamental theorem for calculus. Do you still remember fundamental theorem of calculus or not? The normal one. It's FTC. Anyone can recall? What is FTC? Not UTC, yeah. UTC. Yeah. This one is very classic result and a very important result. This is how you do integration actually. Yeah. So if capital F is an antiderivative of xx, so what does this mean here? Am I writing the wrong thing? It's the antiderivative. So f prime x equals to fx. So fx is the derivative of f prime x. So fx, okay, sorry. Little fx is the derivative of capital Fx. So this means that the capital Fx is the antiderivative of little f. Okay? On some interval. Then, for any a b in the interval, we can do integration. Okay? Definite integral from a to b of little fx. Okay, what do we get? This is equivalent to the capital Fx dx. Okay? So, I will get fb minus fa. This is what you do. This is what we always do. Right? Okay, we evaluated at the two endpoint and then take the difference. Okay, this is what we have been doing. So now we want to upgrade this to a higher dimensional. Here, this f is going from R to R. How about Rn to R? Okay, what's the thing that replaces the gradient here in higher dimensional? What's the thing that replaces this derivative in higher dimensional? What's the higher dimensional derivative? How you differentiate a vector function? Not vector function. Yeah, vector function. Not vector field, vector function. Huh? Yeah, differentiate every entry, right? Differentiate every entries, right? Okay. So what do we get in this case? So what we consider here is the gradient of f now. Okay, we consider the gradient of f. Okay. So if we integrate a gradient of f, we get back the f. Okay. Yeah. So evaluated at the endpoint minus f evaluated at the initial point. Okay. So instead of f prime here, it becomes the gradient of little f. Okay. I want to quickly see why is this true. Okay, let's quickly see why is this true. Okay, let's show this quickly. using the FTC. So let's quickly do this. So note that we still have a dot product here. Okay, we still have a dot product here because the integral we compute should be a number. Okay, so that's why we have a dot product here. Okay, so what is this? So you need to spell out. Okay, spell out what this object is. Okay, what is del of f at r? Okay, so we have to parameterize our r. So the r is parameterized by where's my r? So r t equals to xt, yt, and zt. It's not given, okay? But we know that our t is going from a to b. Okay, so our time variable is going from a to b. What is del f? Del f is del f is it's the gradient. So gradient is del f over del x, del f over del y, comma del f over del z. Okay. How about dr theta? Dr theta becomes what? Becomes del dx over dt, dy over dt, and dz over dt. Okay. Since we change variable to t, right? So it becomes dt. Okay, instead of dx, dy, dz. All the x, y, z will depend on t now. Make sense? Okay. 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 Yeah. Okay. So in this case here, I think this is kind of familiar. What is this? Looks a bit familiar, this one. df dt. Yes, this is df dt. Okay. So this is a differential f evaluated at rt with respect to t. This is what? This is the chain rule. Okay. But in this case here, this case we can use FTC now. Okay, because this is one variable. So we can use FTC now. So this is equals to f of rt from A to B. And this part we use FTC. Okay, so this is F B minus F R A. Okay, this is what we want to get. So the higher dimensional fundamental theorem is derived from the lower, from the one variable FTC. Okay, fundamental theorem for line integrals. Okay, okay. All right. So how are we gonna use this? So let's try and compute this. Calculate the dot product here. So you should think of this as what? Force dot with a displacement. This is a work done. Okay, we try to compute this work done here. Where the vector field is this R over R norm of R cube. Looks familiar or not? What is this? Look familiar or not? R over R cube. This is the potential function for your gravitational field. Okay, potential function for your gravitational field. And C is a smooth curve from 3, 4, 12 to 2, 2, 0. That does not pass through the origin. Why doesn't pass through the origin? Why is the origin important here? Huh? What happened? What happened near the origin, that function? The force. Yeah. Close to zero. What happened? Something very small divided by something even smaller. So you will approach infinity, okay, when you go to zero. So they want to avoid this thing to happen. Okay, so they don't pass through zero. Okay, so what? So how do we compute this function here? We are trying to use the fundamental theorem for line integral. Okay. So from just now, right? From this morning. Okay, from this morning. What do we know? From this morning, we know that FR is conservative. What does conservative means? That is, FR equals to the gradient of some scalar field. Correct? Remember? Okay, I think the other way around. So, wait, let me think. So F is a vector field. Yes, correct. So yeah, correct. I think it's correct. Okay, yeah, correct. So it is the gradient of some scalar field. Okay, what's the scalar field we have this morning? Anyone still remember? Then the one that Jinsen differentiate one. Forget already? Which one you differentiate in the morning? What's this F here? Gradient of which function field? C over square root of x squared plus y squared plus z squared. This one. Clear? Okay, so this is the scalar field. So we can write it as integrate C of del F dot theta. Okay, so when you see this del F, right, you should think of the lower dimensional case one, F prime. Okay, so F prime, capital F prime. Okay. So in this case here, what happened? How to integrate this? This is what? Integration of derivative. So it's just the antiderivative. This is the antiderivative. Yes, it's the antiderivative evaluated at the ending point minus the antiderivative evaluated at the starting point. Okay, so it's just F apply on the ending point. Where's the ending point? 220, and then minus F evaluated at the starting point. Okay, so what do we get? So we get C over square root 2 squared plus 2 squared plus 0 minus C over square root 3 squared plus 4 squared plus 4 squared. So altogether we get C times 1 over 2 square root 2 minus 1 over 13. Okay, no? So you see, this integration here actually doesn't depend on path. Doesn't depend on path. Other than this path have to avoid the origin. That's all. Okay, can you see or not? Can you see this? This doesn't depend on path. So you see, let's see, this is the origin. Okay, where is 3, 4, 12? Okay, let's maybe this way. And then 2, 2, 0. So just now when we do line integral, right, we need to parameterize the curve. But this computation here doesn't involve curve. It just involves the end point. Okay, so if you go the left way or you go the right way or you go like this, they are the same. Okay, for C1, C2, C3, they are all the same answer, regardless which curve you pick. If your vector field is conservative, okay, if your vector field is conservative, your line integral doesn't depend on path. Okay, you just need to know where it starts, where it ends. Right. Remember just now in the morning we computed a line integral. They have the same end point and starting point, but they have different path and leads to different line integral. But now we have the same regardless which path. If your vector field is conservative. Okay, no? Okay. Make sense or not? Yeah. Okay, so if your vector field is conservative, then your line integral doesn't depend on curve. It not only depends on the starting and ending point. Okay. Any question or not? Maybe we go a bit longer and then maybe. Is your brain still okay with a proof or not? Or need to take a break? Huh? Want to test your limit? Can. Okay, let's do one proof and then we take a break. Okay. Okay. Okay, let's continue first. So we say that a set is connected, okay, if any 2 points in D can be joined by a piecewise smooth curve lying entirely in D. Okay. So when we say a set is connected, so this is an adjective for a set. How is it connected? I take any 2 points in D, okay, I can walk to the other point, okay, using a path. Okay, path connector. So let's check between A, B, C, D, E. So these 4 cases, which one is connected? Is A connected or not? Is A connected? So if you pick any 2 points, can I walk to the other point using a path? Okay, so this is connected. Is B connected or not? Yeah, what's the black line mean? Black line means you cannot pass through this point here. Huh? You cannot pass through this black line. Is it not connected or not? If I pick one point here, if I pick another point here, can I walk through? Can, right? I just need to walk a longer path. Yeah, white area is the complement. Okay. Okay, still connected. Okay, the second one still connected. How about C? Also connected, right? So if I pick any 2 points on the yellow region, I can just connect by some smooth curve. Okay, connected. D? Connected. E? No, right? Okay, I cannot walk from E1 to E3, okay, by making curve. You see, some curve have to stay inside the white region. Okay, so no, so not connected. Not connected. So how to prove? You need to find not connected means there exists 2 points such that it cannot be joined by piecewise smooth curves that entirely lie inside the set. So you just pick 1 point from E1, 1 point from E2. Then there's no curve that join them. Okay, and this E1, E2, E3, E4, right, is what we call the connected component. Okay, so there are 4 connected components here. Because within E1, it is connected. Within E2, it is connected. Within E3, it is connected. Okay, so we will say that here there are 4 connected components. Yeah. Okay, and then another thing is a curve is closed. Okay, a curve is closed if the terminal point coincide with the initial points. Okay, so this is the point is closed. Now you can compare the closed set definition with this closed. Okay, you can try and compare these two. What's the similarity? Okay, does one imply the others? Right. What's the close in the definition I gave last time? A set is closed. Complement of the it is a complement of an open set. So since this curve is closed, right? Curve is a set of point. Is this curve here complement of some open set or not? What is the open set you can take away from R2? Okay, so it's C. So this, let's say this curve is called C. Is this equal to R2 take away some open set or not? And what's the open set you should take away? Yeah, anything beside the curve. Right? Should be anything beside the curve. So here and then here. Okay. Okay, let's continue. So let's finish up this and then prove one theorem and then we can take a break. So this line integral, okay, is said to be independent of path in the connected set. So why we want connected set? Because we want to talk about path. So we need to be able to form path always. So we want a connected set. So an integral is independent of path if any 2 points in D, okay, because it is a connected set, I can form path. The line integral has the same value for every path from A to B in D. Okay. So why I need the connected concept, connectedness concept, because for any 2 points in my set, I want to form path so that I can do line integral. Okay. So a line integral is independent of path if for any 2 points in my connected set, the line integral will always has the same value no matter what path we pick. It just depends on the endpoints. Okay, starting point and terminal points, ending point. Okay. Okay, next proof is quite important. Exam will have this. So we're trying to prove this. So the line integral f dot dr. So this is a word done. Okay, f dot dr is independent of path if and only if this word done is equal to 0 for every closed path. I want you to stare for a while this statement. Roughly think about it. Why is it true? So first statement is you take any 2 points, okay, and then you join them anywhere you like. You should get the same value for your line integral. Second, if you integrate over a closed path, okay, your endpoint and starting point is the same. Then you will always get 0. Okay, how they imply each other? Okay. Should we take a break? Because I introduced quite a lot of definition just now. Let's take a break until 2:19. We'll prove this.
因为太晚，我们讲到英文啊，好，电电成你讲，我是电有那个机会。
这个你可以了，
我可以的，可以的，我可以，越没就好。
这可以全面爆炸了，感觉。
叫你叫你讲你讲一点对。哪个的？跟这边不一样啊。为什么？我是喜欢都有。
讲。How's third one yet?
哦，
下个没事。
可是这个你用那个 text maker 或者 text filter 的话，它直接会出在你打 text 的那个地方，那个 text bar
结束，
一出就能直接说。
我就是再见。
我很少都是我都有碰完全不用那个，然后我就点我说那他挂了就。哎，但是我可以说的，是吧？太傻了，就是我看我是利用带一个节气，
但是还是什么？
其实里面写
没有。
可以改吗？
还是那个什么缺词，什么什么缺词，那个缺词对的。
我觉得我现在会爆炸。
然后那个学期都是
每个学期两个专业的特点。期中考试之后就开始了。
对的，
没有感觉吗？
下次可以
下的题就很多。
那我今天的读过的，OK，丢过对完了。
我现在就已经。
这个
每个我们现在那个每个礼拜都有。
而且还挺费事儿。
啊。
你是打掉了，为啥？
你们现在我在我这边找现在就是
都很多。
或者你用这种有出来
我检查很假吧？我就应该我就碰到我就我就知道。
说一下面那
因为你这个是学到其实还没
是，你也可以看懂，但是可能想不出来思路。但是algebra 你连题都看不懂。
一路看不懂，懂忘记。
这种
你跟上英文的会偏协调是一个选择，跟他讲时间。
可以问一下同学不懂啊？
三个知道，你三个知道。
课人越上越少，越上越少，大家后来都不去了。问问他。
我那些报不可以，现在我还另外加一个 paragraph 来 explain 它可以。
OK， 等一下我慢点再跟你讲。Hello。把 PPT 的打进 report。Yes. Yes. 你就 report the format. So report format for your report 2, right? Hello. Are we starting? Let's start. So for your project 2, the format is you put a problem statement, okay, one section, what you want to solve, and then second, you write down the solution, okay, how you solve it. Okay, two sections only in your report 2. Does it make sense? Okay, yeah, problem statement, one section, and then solution, one section. And then inside solution, you use your theory, partial derivative, sequence, or what. Okay, yeah. Only 2 sections. If you have reference, then you make another section for your reference. Okay? Okay. Okay, let's try and prove this. So there are 2 directions here, if and only if. Okay? So we will prove one direction first. So let's prove going from the left to the right. So going from left to the right, we want to show what? We want to show that the line integral over a closed path is always 0. Alright, so there's a trick here. Here we can play some trick. So what's the closed line, closed path we can consider here? Okay, we can split our closed path into 2 parts. Okay, call it C1 and C2. Okay, in the domain D. Okay, how we define C1 and C2? Where C1 starts at A and ends at B, and then C2 starts at B and ends at A. So this is exactly what is on the left hand side here. So I have a closed path C. Okay, I split it into half. Okay, I split it into half. Okay. Why do I do this? Remember that last time there's an additivity property of my line integral. Okay, if I split my curve into piecewise smooth, Ivan, can you close the door? Thank you. If I split my curve into piecewise smooth curve, I can split the line integral into multiple line integral on the piecewise smooth path. Okay, so C1 is going from A to B, okay, but C2 is going from B to A. The assumption is what? The line integral f dot dr, the work done, is independent of path. Meaning what? If you start at A, ends at B, you will always get the same line integral no matter what path you take. But you know that C1 is from A to B, C2 is from B to A. Are these two integrals related or not? They have the same endpoints, but the endpoints swap. Can I swap it back or not? I can change the orientation of C2. What happens if I change the orientation of C2? You will get the integration of the negative C2 to be the negative of integration of C2. Okay, so I can make my C2 to start with A by changing the orientation. So then in this case here, both C1 and minus C2 are starting from A and ends at B. But we know that these two integral is the same. Okay, so we have this equal to 0. Since the line integral is independent of path. Make sense or not? Okay. Independent of path means if you have integral from the same endpoint, from the same starting point and at the same endpoint, the line integral will be the same value. Okay. So you are taking difference between same values, so you get the 0. Okay. Okay. So one direction done. How about the other direction? So we want to show that the line integral is independent of path. So how to prove this? So you need to take for any 2 points, okay, consider any 2 paths, show that the 2 line integral is the same. Okay, how do you do that? So first of all, you need to start with any 2 points, okay, and then you need to pick any 2 paths. Okay, and then show that the line integral over these 2 paths is the same. But your assumption is you have line integral over a closed path. Can you make a closed path out from these 2 paths or not? Can you make a closed path out of the 2 paths here? So both paths is going from A to B. Can you make a closed path here? No? Closed path means what? You start with A, end with A. Can you make a closed path that start with A, end with A using C1, C2 here? Yes, you can go from A, go from C1 to B, and then work backward from C2 to A. Okay, I don't want to do C1, right? If I go C1 and then come back C1, then these 2 line integrals should be the same because by the orientation. But how about we take C2 and then return from take C1 first and then return from C2. Okay, then we will get a closed path. Okay, so for any 2 paths, C1, C2 connecting A. we can take C1 union minus C2 as the closed path. Okay, but by assumption, the line integral over this closed path is 0. Yeah. Okay, by assumption, this integral is 0. But by the additivity of line integral, I can split this line integral up to 2 parts, right? C1 and minus C2. Okay, but by the orientation again, orientation of the curve, I can move the negative out. Okay, so the difference of these two line integral is 0, meaning integral over C1 is the same as integral over C2. Okay, now. Okay. Okay. So this proof is very important for your exam. Okay, you must understand this. Okay, now. Okay. Any question on the proof? I think quite straightforward, right? So the trick here is how you form a closed path, okay, from 2 paths, and then how to split a closed path into 2 paths. Okay, yeah. How to split closed path into 2 paths, how to join 2 paths into a closed path. Okay, other than that, then it's just a property of line integral. Okay. Okay. Okay, next part, independence of path theorem. So again, the work done is independent of path if and only if you can write your vector field as your vector field is conservative. Okay, so just now we see one direction already, right? If my vector field is conservative, I compute the work done, I can just use the FTC to compute. Yeah. So one direction we have done. So if we compute a conservative, compute the line integral of a conservative vector field, this we can compute using the fundamental theorem of line integral, okay, where we get f evaluated at the starting point. How should I denote this? Hey, how should I denote this? Should we denote this? Okay, let's call it B and A, where B is the terminal point of C and A is the starting point of C. Okay, so by the fundamental theorem for line integral, we don't need to care about the parametrization of C. Okay? It's just the difference at the starting point and the end point and the starting point. Okay, this is one direction. The other direction is harder. I don't want to discuss now, but I will put out the proof. Okay, for you. Okay, only the proof that I done in class is important. If not done in class, then you can ignore if you like. If you want to study, then it will be good. It will be interesting to discuss if you want. Be interested to discuss. Okay, so this is also a if and only if result here. Okay, so very important here. This is also an if and only if result. So you have 2 if and only if result with the independent of path line integral. Okay, so one is if you integrate over closed path is always 0. Okay, then your line integral is independent of path. Or if your if and only if another thing is your vector field is conservative. So these three are equivalent. Okay, so let's make a summary here. So if you have a continuous vector field, these three condition here is equivalent. Okay. If your vector field is conservative, then the line integral is independent of path. The line integral over the closed path is always 0. Okay, so these three things are equivalent if and only if. Okay, no? So these three very important. I think we will use it again. There's another property popping up again to see whether the F is conservative. Physicists are interested in this conservative vector field because energy is conserved under this vector field. Okay? Okay. Okay. So, let's continue. So we will introduce what a simple curve is because later we'll introduce more stuff. So a simple curve is a curve that does not intersect itself anywhere between its endpoint. Okay, so the first one is simple, okay, because it doesn't intersect itself. It's not close because the endpoint and the starting point is not the same. The second here is not simple because it's intersecting itself. Okay, and it is not close either because the starting point and the endpoint is not the same. And the third one is simple and close because it doesn't intersect itself. But the starting point and the endpoint is the same. You can pick anywhere to be it starting or endpoint. Okay. Fourth one is not simple because it's intersecting itself but close. Okay. Yeah. So you can see that this diagram are drawn in 2D. Okay. So typically when people want to resolve this, we call it a singularity. We can put it in a higher dimensional. We can leave this intersection away. Okay. So imagine like this. Okay, you see. I'll see here. So you can see that this line here, maybe it's intersecting here, right? But if I go to higher dimensional, I can pull this intersection away. Such that it doesn't intersect. Okay. So what we do in algebraic geometry is we call it a blowout. Okay, we blow it out. Okay, from this way, maybe it's intersecting, but I blow up this way. Okay, no, I can leave out the intersection. Okay, but you need to do it in a higher dimension. Okay. Okay, next. Simply connected domain. So what is simply connected domain here? So they're connected. Okay, so first of all, it is a connected domain. So recall what is connected domain. Any 2 points, I can join with path. Okay, smooth curve. So what is a simply connected domain? So it's a connected domain where one can continuously string any single closed curve into a point while remaining in the domain. So out of these 4 shape here, this one is simply connected because you can take any simple closed curve and then you string it into a point. Okay, you can string to a point. So let me draw again. So like this. Okay, you can string to a point. Okay. How about they say that this 4 is not simply connected, right? So why? So the first one, why this is not simply connected? Is it connected or not? Connected, right? If I pick any 2 points, I can join with a path. Okay. Why is it not simply connected? Where is the simple curve that I cannot string down to a point? Huh? Straight line? Straight line is not a closed curve, right? I need simple closed curve. Straight line is you can shrink to a point, right? Straight line, you can just shrink to a point. Okay. But I want simple close. Simple mean doesn't intersect itself. Close mean a loop. And so if you form a loop here, you can shrink to a point. You can just shrink to the center. Okay. So which closed curve I cannot shrink? Yes, I can draw one around the hole here. This one cannot shrink to a point. Can you shrink to a point? You cannot. Okay, you cannot shrink this curve into a point. Because there's a hole here that you cannot pass through. So you can see that if I shrink this simple closed curve as small as I can, I still loop around this curve here. I cannot go further. Okay or not? For example, a simple closed curve here, I can shrink to a point because I can consider this series of closed curve. Okay, but here I cannot. I can go as small as this curve, this hole here. So I cannot shrink to a point. Inside the domain. Okay, it will remain as a curve like this. I cannot shrink it further. Okay, how about the second one? Okay, there are more curves that you cannot shrink. So you cannot shrink this curve down to a point. You cannot shrink the other curve that enclosing the other hole. And you cannot shrink the other curve that enclosing this two hole here. Okay, the smallest you can go is like this. Okay, the smallest you can go is like this. If you're going to shrink the curve that enclosing two holes here. Okay, you can imagine you can do this. Okay, and then do this, and then do this. Okay, and then the third one, it is simple, but it is not connected. Okay, so this subject is actually a algebraic topology, if you have chance to learn it. Okay, in future. This is an algebraic topology. Okay, okay, so this is simply connected. All right, so why we need this? Because of this theorem here. Let F be a vector field on an open, simply connected domain. So last time we talked about open set, right? Okay, you can, for every point, you can find a neighborhood. Okay, that's such that the neighborhood lives inside your domain. And then simply connected. Okay, so meaning any closed curve, you can shrink it to a point. Okay, simply connected. And suppose that f1 and f2 have continuous first order partial derivative, then f is conservative if and only if. Okay, if and only if what? The partial f1 with respect to y equals to the partial f2 with respect to x. Okay, you can notice that these two variables kind of swap position because f1 is the x component, f2 is the y component, but we test it with a opposite variable. Okay, only these two are equal, then f is conservative. Okay, so you wonder, hey, where this open simply connected involved? It's involved in the proof, but we don't care about the proof. Okay, but you will see that all our question is open simply connected. Okay, you will notice this. Okay. So remark, f is conservative implies this equation here. Del f1 over del y equals to del f2 equals to del x. But one direction you don't need the condition, but the other direction you need. Okay. The other direction you need open simply connected. One direction you don't need. Okay. Conservative imply the equation, maybe you don't need this condition. But if you want to go from the equalities to conservative, then you need this open simply connected condition. Okay. One direction you don't need, the other direction you need. Actually, this is something to do with your ODE. ODE. I don't know, you have yeah, the exactness is this thing. Yeah, the exactness stuff is this thing. I think I have demonstrated them a proof for ODE using this. Let's see. Amazing. What's the statement? Okay, maybe I try and find it next time and then I show you. It's something related to the exactness you learn. And then we will prove it more quickly in the vector calculus. Because in ODE, you have to integrate in one direction and then integrate with respect to the other direction. I think you'll call it integrating factor. Yeah. Okay, anyway, we will see it, I think next lecture. I remember I showed them once. Okay, let me see. So if you go to higher dimensional, right, you have more equations to need to check. Okay, you have 3 equations that you need to check. Okay, 2 more equations you have to check. Okay, for vector field in 3-dimensional to be conservative, you need to check 3 conditions here. We will meet this again. Okay, we will meet this again. It's related to Green's theorem stuff. Okay. Okay, so let's do one example. Try and determine whether this vector field is conservative or not. If yes, find x potential function. Okay, I think from this example, you should recall something from your ODE. So how to check conservative? Okay, just now we say that if this is a two-dimensional vector field, only one equation you need to check. You just need to check del f1 over del y is equal to del f2 over del x or not. I do this 2 computation here. Is it equal? Del f1 over del y, what do you get? Del f1 with respect to y. 18 s squared 1. What about del f2 over del x? 18 also x squared y. Okay, so they are equal. So it is conservative. But you still need another condition, right? You still need whether this function works in the open simply connected set or not. Remember? You have to have your vector field on the open simply connected domain. Okay, only you can check these 2 conditions here. Okay. Yeah, your vector field must work on the open simply connected domain. Okay. But the domain we consider here, it doesn't mention. So if it doesn't mention, we will regard this as the whole R2. So is R2 open simply connected or not? It's open, right? Because it's the whole space. Okay. Is it simply connected? Yes. Okay. If you form any simple closed curve inside the R2, you can string the circle into a point. Okay, you can string the circle into a point. It's open simply connected. Okay, so F is conservative. So F is conservative means what? It is a gradient of some scalar field. Okay, it's a gradient of some scalar field. Okay, remember the example of the gravitational vector field? It is a gradient of some scalar field. So how to find the scalar field? So you have an equation here. So F, the vector field here is equal to the gradient of some scalar field, which is the vector del F, del X, comma, del F, del Y. Okay, I want to find this vector F here, but we know what is del F, del X, and del F, del Y. Okay, this is given, right? This is given. This is just F. Okay, so we know if we want to differentiate the little f, the potential function with respect to x, we know that it is actually 4x cubed plus 9x squared y squared, comma, del f del y is 6x cubed y plus 6y. Okay, we have two equations here. Okay, we have two equations here. Two partial equations here. And del f del y equals to 6x cubed. Should we do this? Let me think. Okay, let me think. Yeah, so this is true. Yeah, okay, so this is true. Okay, we have these two differential equation here. So what can I do? I can try and integrate. Okay, I can integrate one of them. So let's say I integrate this one with respect to x. And then we integrate with respect to x. So what do I get? I actually get x to the power 4 plus 3x cubed y squared. Okay, plus some constant. And this constant here is could be a function in y. Because remember, if you differentiate this function with respect to x, all the y will disappear. So maybe you have some y involved in this function here. Okay or not? Does it make sense? Make sense? Okay. And then again, you can go from this y reduce down to df partial derivative with respect to y. Okay, I can differentiate this with respect to y, which I get. What do I get? Sorry, 6x cubed y plus g prime y. Okay, then I can compare the two I have. So I can compare these two things I have. Right. So this implies what? This implies that g prime y equals to 6 to the y to the 5. And then I can integrate this again. So I get gy equals to 6 to the y to the power 6 plus c for some constant c. Okay, so together I get fxy equals to x to the power 4 plus 3x cubed y squared plus y to the power 6 plus some constant c. Okay, is it similar to the calculation you have done in ODE? Right. Okay. All right. So if you have shown that this is a conservative vector field, then it is easy to compute the work done. You can use the FTC to compute. Okay. Apply FTC on this potential function here. So this scalar here doesn't affect your computation, right? At the endpoint, you have C. You minus the C in your starting point. So C and C will cancel out. Okay. It's okay that we don't know about the C, but the C will cancel out in the integration. Can see or not? Huh? Can see? Yeah. If not, you try first and I will post out the solution. Any question? No? Hey, why not teacher now? Can I go longer? actually couldn't go too long anymore. Almost finished this part. I thought it's 1 hour later. Okay, so why we call it a conservative vector field? Because it has something to do with the conservation of energy. Okay, if you compute the energy, potential energy and kinetic energy involved in this force field, they are conserved. Okay, that's why this vector field, we call it a conservative vector field. Okay. Okay, this part is not important, just to motivate why we call it a conservative vector field. Okay, any question about this showing some vector field is conservative? So for yeah, Jinsen, any question? Why you laugh? Why you laugh? So what I want to say is, if you want to check whether a vector field is conservative, for two dimensional, you just need to check one equation. Okay, for 3-dimensional, you need to check 3 equations. Okay, for higher dimensional, you should check more, but we don't care. We only care about R3. Okay, there's one exercise on the R3 you can try. Okay, okay or not? Okay. If no question, next week we will proceed with Green's theorem, and then let's see, divergent and curl. Okay, divergent and curl, Green's theorems. To prepare to facilitate the teaching speed, right? You can try and read the parametric curve first. That part we will go quite fast because because we just want to use it. Okay, you can read the 16.6 part. Okay, we will go quite fast as like how we go through the parametric curve. Okay, so it's like we parameterize curve at first, then we parameterize the surface. So curve you need one variable, surface you need 2 variables. Okay, so we don't just look at xy plane, we want to look at curve xy plane. Okay, so we use UV, but UV appears in a different form. Okay, no? Okay, and then we will see you next class. So next class is until 6, right? I'm not sure. Maybe we will try and extend half an hour. Maybe. It depends on the speed. Okay. Hopefully we can done all this in the 2 lectures. Okay. Hopefully. Huh? Is it? Okay. Okay. So make sure you go and try the question that I haven't touched, and then if you have problem, then we can discuss next lecture. Okay. Otherwise, I will post the solution and then see you understand or not. If not, we can discuss. Okay. Yeah. Okay. Okay. See you next week.